So, welcome to this deep dive. Today we're getting into something that sounds simple but is actually totally wild.
Yeah, we're talking about perimeter, area, and volume.
Right, which, if you're prepping for the TEAS or the HESI nursing entrance exams, you absolutely need to know this stuff. But our mission today isn't just to force you to memorize a bunch of rote math formulas.
No, definitely not. We're actually diving into the history of measuring space because it's epic. It involves philosophical crises, ancient mythology, and even exploding spaceships.
Which is crazy to think about because, well, usually when you step into a standard hospital room, you just expect everything to be completely precise.
Oh, totally. You inherently expect the physical space to just be mathematically settled.
Exactly. Like you look at the exact dosages in an IV or the perfectly squared off floor tiles. But the deeper you look at how humanity actually figured out how to measure all this, that concrete floor starts feeling surprisingly unstable.
It really is a mathematical rabbit hole. I mean, what we consider simple geometry caused literal intellectual meltdowns over the centuries.
Okay, so let's set a baseline for you, the listener. Let's use that hospital room. Say it's, I don't know, a standard 12 by 10 foot room.
Sure, 12 by 10.
Perimeter, area, and volume are basically three entirely different physical realities coexisting in that one space. So perimeter is just the 1D linear distance around the edge, right? Like if you were putting a baseboard trim, 12 plus 10 plus 12 plus 10,
Yeah.
44 feet.
Right, it's just a line.
Yeah. And that area is the 2D surface, the actual space covering the floor. So 120 square feet of linoleum. And then volume is the 3D space, filling it all up, the air, the equipment, the capacity.
And, separating 1D, 2D, and 3D space, that sounds so completely intuitive to us now.
But yeah, it's basically elementary school math.
Right, but defining what it actually meant to take up space was historically a massive problem. I mean, if you look at the ancient Egyptians or Babylonians, they didn't really care about the philosophy of it.
They were just trying to survive, right?
Exactly. They were purely practical. They needed to tax farmland based on its size, and they had to, build granaries to hold the grain.
So they weren't sitting around debating the fundamental nature of reality.
No, not at all. They just needed formulas that worked. There's this document, the Rhind Mathematical Papyrus, from around 1650 BCE in Egypt, and it has a formula for the area of a circle.
Oh, wow.
Yeah, and they basically approximated the area by taking 8/9 of the diameter and squaring it, which, if you run the math, implies a value for pi of roughly 3.166.
Wait, really? That early?
Yeah, and the Babylonians were doing something really similar on clay tablets using an approximation of 3.125, which is remarkably close to the true 3.14159.
Especially considering they didn't even have a formal concept of pi as a universal constant yet.
Right, they were just reverse engineering it through trial and error.
Which is super impressive.
Yeah.
But I'm guessing that whole close enough mindset didn't fly once the Greeks showed up, because the ancient Greeks don't exactly strike me as the close enough type.
Oh, they absolutely were not. Starting with Eudoxus in the 4th century BCE, and then formalized by Euclid around 300 BCE, they demanded rigorous proof.
Like absolute mathematical certainty.
Yes. To Euclid, a shape's area wasn't just some number you got by eyeballing a wheat field. It was a profound geometric truth. You had to derive it step by step from foundational axioms.
Which he put into his famous book, right? The Elements.
Exactly. Books I and II establish basic area equivalences, like proving a triangle is exactly half the area of a rectangle with the same base and height.
Okay, but how did they prove the area of something curved? Like a circle? I mean, they didn't have calculus.
No, they used something called the method of exhaustion.
Method of exhaustion. That sounds tedious.
It was incredibly tedious. Imagine a circle, right? Now draw a triangle inside it.
Okay, got it.
The triangle's area is easy to calculate, but it leaves a bunch of empty curved space around the edges. So you change it to a square, then a pentagon, then a hexagon.
Oh, I see. So as you keep adding more and more straight sides, the polygon pushes out closer to the edge.
Precisely. You are literally exhausting the empty space until the polygon effectively becomes the circle.
Wow. Okay, so that held up for a while, I imagine.
For nearly 2,000 years. But eventually, the definition of area had to shift. If we connect this to the bigger picture, the crisis really started when mathematicians like Newton and Leibniz developed calculus in the 17th century, specifically integration.
Oh, integration. Yeah, I vaguely remember that from high school. That's finding the area under a squiggly curve on a graph, right?
Exactly. Calculus basically allowed you to compute the area of totally fluid, irregular shapes by mathematically slicing them into infinite tiny vertical slices and then adding them all up.
That sounds like a massive leap forward.
It was. But it also set a trap, because mathematicians started assuming that every conceivable shape must have a clearly defined area or volume.
Let me guess. They were completely wrong.
Spectacularly wrong. In 1902, this French mathematician, Henri Lebesgue, triggered a full-blown math crisis, because before him they used the Jordan measure for area, which basically trapped a shape between a grid of boxes inside and outside.
Kind of like a modern version of the exhaustion method.
Right. But Lebesgue proved that there are these bizarre, infinitely jagged, theoretical geometric sets where that logic just completely breaks down.
What do you mean breaks down? Like it doesn't work.
Right, like imagine a shape that is just an infinitely scattered dust of points interwoven with empty space. You literally cannot trap it inside any boxes. Under the classical rules, these shapes simply had no well-defined area or volume at all.
Wait. So like professional mathematicians prove that the fundamental concept of area is just broken.
For certain theoretical shapes, yes. Lebesgue had to invent a whole new framework called measure theory to fix it, which assigns a mathematical weight to sets of points instead of looking at physical boundaries. It's highly abstract, but it's the modern foundation.
Okay, I feel like I need to jump in here and just reassure you, the listener. If you are prepping for your TEAS or HESI right now, please do not panic.
Oh, yeah, no need to panic.
Yeah, you do not need to know Lebesgue's measure theory. The exam is not going to throw some infinitely jagged theoretical dust cloud at you. For clinical nursing math, the classical Euclidean formulas are all you need.
Thankfully, yes. Euclidean geometry is perfectly safe for healthcare.
Good. Because, look, anyone taking these exams already knows the area of a rectangle is length times width. We've had that drilled into our heads since, what, 4th grade?
Definitely.
But I feel like memorizing a list of formulas like a robot is exactly how people freeze up on these tests. So let's look at why they work.
I love that approach, because mathematics is incredibly visual.
Yeah, so let's run through them. We've got the big ones. Rectangle is length times width. Square is just the side squared. Triangle is 1/2 base times height. Parallelogram is base times height.
And then there's the trapezoid, which always trips people up.
Oh man, the trapezoid, it's 1/2 times base 1 plus base 2 multiplied by the height.
Right, which sounds like alphabet soup.
It totally does. But if you visualize it, it's actually so simple. A trapezoid is really just a rectangle that's wider at the bottom than at the top.
Exactly.
So if you just mathematically chop off the wide bottom corners and sort of flip them upside down to fill in the narrow top corners, you just built a perfect rectangle.
Which is exactly why the formula has you average the two bases. You're just finding that middle ground to square the shape off.
It's just finding the hidden rectangle. And when you move from 2D area up to 3D volume, it's the exact same logic. Volume just asks, basically, if I have this 2D base, how many layers of it are stacked up?
Yes, you're essentially just dragging a 2D shape through the third dimension.
Right. So a rectangular prism, like a cardboard box, is just a flat rectangle base multiplied by however high you stack it. Length times width times height. A cylinder is just a flat circle pie squared dragged upwards. So you multiply it by the height.
It's mathematically very elegant. And, understanding how these 3D shapes relate brings us to probably the greatest mathematician in this history, Archimedes of Syracuse.
Oh, Archimedes, 3rd century BCE. Right.
Yep. And his absolute greatest pride was proving that the volume of a sphere is exactly 2/3 the volume of the smallest cylinder that can contain it.
Which is wild to figure out without modern calculus.
It is. He even requested that a sphere inscribed in a cylinder be carved onto his gravestone. And over a century later, the Roman orator Cicero actually went hacking through the brush just to find this overgrown grave and see it.
That's dedication. But here's where it gets really interesting for clinical practice. Archimedes was obsessed with volume, and there's that famous legend about him and King Hiero's crown.
Ah, yes, the story recorded by Vitruvius.
Right, so King Hiero II gives a goldsmith some pure gold to make a crown. But when it's done, the king gets paranoid. He thinks the goldsmith stole some of the gold and swapped in cheaper silver.
But he can't prove it because the crown is intricately shaped. You can't just measure base times height on a bunch of spiky gold leaves.
Exactly. So he asks Archimedes to figure it out. And Archimedes is supposedly stressing about this, and he goes to the public bathhouse. And as he steps into the tub, he notices the water level rising and spilling over the edge.
The displacement.
Right, he has this massive epiphany. The water being pushed out of the way is exactly equal to the volume of his own body. He supposedly shouted, "Eureka!" and ran home naked through the streets.
Well, streaking or not, he had discovered indirect measurement. He realized he could dunk the complicated crown in water, find its exact volume from the displaced water, and then divide its weight by that volume to find its density.
Catching the thief. But the coolest part is that indirect measurement through displacement is real physics used every single day in healthcare.
Absolutely. Let's ground this in a real clinical scenario that you, the listener, will actually see on your exam. Let's say you have a cylindrical medication vial. The internal radius is 1 centimeter, and the liquid height is 5 centimeters.
Okay, let's do the math. Base is pi times radius squared. So pi times 1 squared is just pi, roughly 3.14.
Right.
Then you multiply that by the height of 5, which gives a volume of about 15.7 cubic centimeters.
And here's the vital translation for nursing. 1 cubic centimeter of space, which we often call a cc, is exactly equal in volume to 1 milliliter of fluid.
Wait, exactly.
Exactly equal. They are completely interchangeable units. So that vial holds exactly 15.7 milliliters.
Okay, that makes so much sense. Like on those old medical TV shows where they yell, give me 50 cc's of saline stat. A cc is literally just a cubic centimeter. That is the exact bridge between 3D geometry and fluid dosages.
It is. But, and this is a big but, knowing the formulas is only half the battle, because where people make truly catastrophic errors is when they fail to understand how these dimensions scale.
Oh, scaling. Yeah, this always messes with people. Let's test this concept because it is so counterintuitive. If I have a square and I double the length of its sides, I just double the total area, right?
It feels intuitively true, but it's totally wrong. If you double the linear dimensions, the area doesn't double. It quadruples because 2 squared is 4.
Oh, right, because area is two-dimensional.
Exactly. And if you take a 3D box and double its length, width, and height, the volume doesn't double. It multiplies by 8. 2 cubed is 8.
So if I triple the dimensions of a box, the volume goes up by 27.
Yes, 3 cubed. This exponential growth is called the square cube law.
The square cube law. Okay.
And it dictates the physical limits of literally everything in biology. J.B.S. Haldane wrote an essay in 1926 called On Being the Right Size, where he pointed out that those giant human-sized ants from 1950s sci-fi movies are physically impossible.
Because of the scaling?
Exactly. An insect's physical strength depends on the cross-sectional area of its muscles, which is 2D, but its weight depends on its total volume, which is 3D.
So the volume grows way faster.
Much faster. If you scale an ant up by a factor of 100, its muscle strength increases by 100 squared, so it's 10,000 times stronger, but its weight increases by 100 cubed. It becomes 1 million times heavier.
Oh, wow. So the mass completely outpaces the strength.
Its legs would just instantly snap under its own weight.
That's terrifying, but also fascinating. And honestly, this isn't just movie trivia. This applies directly to nursing, specifically with neonates and premature babies.
Oh, really? How so?
So it's the exact same math, just applied to heat loss. A baby is not just a tiny adult. Because they are so physically small, their surface area, their skin, is incredibly large relative to their internal volume.
Ah, I see.
Yeah, adults have a ton of volume generating heat and relatively less skin surface radiating it away. But a neonate has this massive surface area to volume ratio. They radiate heat out into the room way faster than their tiny mass can generate it.
Wow.
Which is exactly why premature babies are at such high risk for hypothermia and need incubators. It is literally the square cube law in action.
That is a phenomenal clinical application. Biology is strictly bound by geometry. But humans forget this all the time, especially when we don't respect the units of measurement. You know, area isn't just a number, it's fundamentally squared. Volume is fundamentally cubed.
Right, and if you just drop the exponent or, mix up the units, everything crashes.
Quite literally crashes. Have you heard of the Mars Climate Orbiter disaster from 1999?
Yeah, that was the NASA spacecraft that basically just burned up in the Martian atmosphere, right? Because it came in too low.
Yes, a $327 million interplanetary mission. And it wasn't a mechanical failure, it was a unit failure.
Wait, really? Just a unit mix-up?
Just units. One engineering team programmed the thrusters using pound force, an imperial unit, but the navigation software was expecting newtons, which is metric. The math itself was completely flawless, but because the underlying units were mismatched, the physical reality was entirely wrong.
Over $300 million lost because of a missed conversion. See, this is why dimensional analysis is life or death in a hospital setting. I mean, confusing a linear measurement with a squared one, or mixing up ml and L, or milligrams and micrograms, it's the exact same category of error as crashing that Mars orbiter.
Accuracy is totally non-negotiable.
A number on your exam without the correct unit is just wrong. In a clinic, it's a lethal hazard.
Which brings up another major misconception students face: confusing volume and capacity. People use them interchangeably, but they are mathematically distinct.
Wait, really? I always kind of thought they were the same thing.
Most people do, but volume is the physical three-dimensional space an object occupies. We measure it in cubic units, like cubic centimeters.
Okay.
Capacity, on the other hand, is how much fluid or gas a container can hold, measured in liters or milliliters.
But didn't we just establish that 1 cubic centimeter holds exactly 1 milliliter?
We did. The numerical value is identical. But conceptually, volume is the space the physical glass itself takes up in the universe, and capacity is the water it can hold inside.
Ah, I see. Okay, so we've talked a lot about volume and the disasters there.
Yeah.
But the relationship between a 1D perimeter and a 2D area actually has its own crazy history. And it moves from ancient mythology straight into modern courtrooms.
Oh, this is one of my favorite historical through lines. We have to look at the founding myth of Carthage from Virgil's Aeneid.
Right. Okay, so Queen Dido is fleeing her brother. She gets to North Africa, and she asks the local ruler for just a tiny bit of land. And the ruler totally mocks her, saying she can only have as much land as she can enclose with a single ox hide.
Which is what, the size of a small rug?
Exactly. Almost nothing. But Dido is brilliant. She takes the oxhide, cuts it into these incredibly thin string-like strips, and ties them all end to end to make one massive cord.
Very clever.
Yeah, and then she lays that cord out in a perfect semicircle, right up against the straight, natural coastline. By using the coast as a free boundary, she maximized the area inside her cord and enclosed an entire hill, which became the city of Carthage.
And that mythological cleverness introduced what mathematicians call the isoperimetric problem.
What problem?
Isoperimetric. The core question is, if you have a fixed perimeter, like a specific length of fence, what shape will enclose the absolute maximum amount of area?
And the answer is a circle. Or a semicircle, in Dido's case.
Correct. The circle is the most mathematically efficient shape in the universe for maximizing area.
I mean, that seems pretty intuitive.
It does, but what's fascinating here is that it took mathematicians over 2,000 years to rigorously prove it.
2,000 years for something that obvious.
Because of those strict rules of proof we talked about. In the 1830s, Jacob Steiner offered a proof that convinced almost everyone. He proved that if a maximizing shape exists, it has to be a circle.
Okay, that sounds like a proof.
But decades later, Carl Weierstrass pointed out a huge logic gap. Steiner never actually proved that a maximizing shape existed in the first place. He just assumed it did.
To a non-mathematician, that sounds like splitting hairs.
To a mathematician, assuming a solution exists without proving it is a fatal flaw. It wasn't until 1901 that Adolf Hurwitz finally used advanced calculus Fourier series to provide a completely airtight proof of the isoperimetric inequality.
Okay, but how does an oxide myth and a 1901 calculus proof actually apply to today? Like, why do we care?
Because it is currently a critical tool in gerrymandering litigation.
Oh, right. When politicians draw those crazy snake-like voting districts to manipulate elections.
Exactly. Now, to be clear, we are just looking at the impartial math here. Courts needed a neutral mathematical way to measure how distorted a district's shape is, so they use compactness scores. The most famous is the Polsby-Popper score, which directly uses this ancient isoperimetric inequality.
Really? How does the formula work?
It takes the area of the district, multiplies it by 4 times pi, and then divides all that by the perimeter squared.
Wait, why is the perimeter squared?
Because of the units. Area is 2D, perimeter is 1D. If you want to compare them without the units breaking the equation, you have to square the perimeter to put them on the same dimensional level.
That is actually brilliant.
It really is, because a circle maximizes area. A perfectly circular voting district scores exactly 1.0. But if a district snakes and sprawls all over the place to capture specific neighborhoods, its perimeter gets massive relative to its area.
Oh, I see. So the perimeter skyrockets, the denominator gets huge, and the score drops close to 0.
Precisely. And courts just use this mathematical inefficiency as circumstantial evidence. It's pure geometry applied to modern law.
That is wild. So what does this all mean for you, the listener?
Yeah.
Let's distill this into the 5 big exam-style takeaways.
Number 1, never mix up your exponents. Perimeter is 1D linear, area is 2D squared, volume is 3D cubic.
Yes. Number 2 is the square-cube law. If you double the dimensions, the area quadruples and the volume multiplies by 8.
Number 3, the isoperimetric inequality. A circle will always maximize area for a given perimeter.
Number 4, memorize the big 3 foundational formulas to derive all the rest. Rectangle is length times width, circle area is pi r squared, cylinder volume is pi r squared times height.
And number 5, arguably the most important clinically. Missing or wrong units cause disasters. Whether it's crashing a NASA orbiter or miscalculating a nursing dose, you have to respect the units.
Exactly, because these are load-bearing tools. If you forget how scaling works, you miss a neonate's risk of hypothermia. If you mix up units on burned surface area, you mess up fluid resuscitation. It all matters.
The math you're learning really is the literal framework of the physical world.
So before we completely wrap up, you mentioned earlier that the concept of measuring space caused multiple crises. Is there like one last mind-bending geometric trap you can leave us with?
There is. So we've talked about perimeter as this fixed, knowable boundary, right?
Right.
But in 1967, Benoit Mandelbrot published a paper called How Long is the Coast of Britain?
I mean, couldn't you just look at a map and measure it?
You'd think so, but he highlighted what we now call the coastline paradox. If you measure the rocky coast of Britain using a rigid ruler that represents a mile, you get a certain number. But if you walk the coast with a 1-foot ruler, that smaller stick dips into all the little crevices and jagged edges that the mile-long ruler just skipped over.
So because it's zigzagging more, the measure perimeter gets longer.
Exactly. And if you use a 1-inch ruler, it dips into even smaller cracks and the perimeter increases again. Because natural coastlines are jagged at every conceivable scale, the smaller your measuring stick gets, the longer the perimeter becomes.
Holy, really?
Yes. The area of the island stays exactly the same, but the perimeter approaches infinity. It never converges on a true number.
That is totally insane. You literally cannot measure the true perimeter of a natural object.
You cannot. This paradox fundamentally broke our understanding of boundaries and birthed the entirely new field of fractal geometry.
Wow. Something to think about the next time you look at a map. Or, step into that perfectly measured hospital room. Appreciate those perfectly straight baseboards, because outside those doors, the boundaries of nature aren't nearly so clean. Good luck in your exams, everyone. You've got this.